So let's start. Last week, as uh, as always, I've been working on the threshold test fix, and one issue was the page interval changed when we still have a pending request waiting for a object context. So the request being executed just bail out and keep retrying, but the ones the pending ones managed to be scheduled before the interrupted ones. So we have an out of order response. I'm trying to reproduce it. Sorry, I'm trying to fix it by introducing a suspend resume semantic in the try mutex. So the interrupted one could have a token when it tried to resume the executing.
And wait a minute.
Okay.
So can you expand on that a little bit? How's that supposed to work?
Again?
What would it mean to interrupt something that currently has the try mutex?
Because I think the PG interval changed. So
you have to start over from scratch. You can't start over in the middle. You have to restart. It's not a resume. It's a requeue and it's a new request.
Yes, by suspend and resume, I mean the ongoing request cannot relinquish the lock. That's the point of.
Oh, I see. So yeah, so so I guess what you need is it to be the case that the interruptible thing, when it notices that, at least when the callback, when that request wakes up and observes that the interval has changed, it needs to drop the lock and requeue itself. Right?
Yes.
Okay.
I don't want to change the code a lot, so it looks like it's trying to acquire the lock from scratch, but actually it should always pass a token to the try mutex, which is set when it is interrupted.
Okay. Is that to ensure that it gets it first? Is that the idea?
Yes, actually, yes. By interrupted, it won't be.
But see, everyone else who's trying to get the lock on the mutex should also fail. That is
no.
Okay. So
they will be appended to the waiting list.
I know that, but they should eventually acquire the lock, observe that the state has changed, drop the lock, and requeue. Because when they started their operation, the PG epoch was whatever it was, and it's not that anymore. I'd like to encourage you to relook at that, because that's a simpler way to make that work. For one thing, you've done stuff before you started to acquire the mutex. You read the object context off disk, you interpreted the I/O.
We wrapped this whole thing in a repeated loop.
Right, so I don't care that much about the way the code is structured. I'm not so worried about. No, you can't just start over. That's the problem. You have to get back into the central wait queue, because everything in front of you also had to restart, and everything behind you. If you simply try to reacquire the lock, I don't think you're ever going to make that ordering work out. Okay, so let's think about the sequence of operations that happens to an I/O. The first thing you do is you put yourself in a queue. Then you come off the queue. It's your turn to run. So you look at the message, you figure out what the object ID is, you read that object context off disk, and then, which is like state that's in memory that you're holding a pointer to. Then it's a shared pointer or whatever. Then you try to take the RW state lock on the object state or whatever, this new try mutex thing, right? So for a read at least, this sequence is pipelined. We might have multiple reads occurring on the same object, and there could be like 10 reads on the very same object blocked waiting for write to complete. So let's say that then the PG epoch changes. It's not enough for the write that's currently in progress to be canceled. All of those reads have to be canceled too.
Hold on. We don't have a write request in the fly when we have a read request.
I know that because the reads are blocked on the try mutex. They started, they tried to get the mutex, they didn't get it, they're blocked. But they are in progress. They're just waiting. That's the entire point of this try mutex.
Right, because they already have the have active PG and
yeah, it's an active
the
PG.
encode number is correct.
Yeah, it's valid to operate. You don't even know whether you have a write in progress until you pick up the object context and look at it. You have to have gotten that far first. That is, it's perfectly fine to have reads and writes in progress at the same time on a PG, just not on the same object. That's why the try mutex is on an object context, right? So when we're looking at a new request that's just come off the queue, we don't even know whether it needs to block until we've looked at the object context, which means that op did some stuff before it blocked. In particular, it has a reference to the object context, which is a shared mutex to actual in-memory state. It has already performed checks related to whether scrub is occurring. It has already looked at the current recovery state of that object and a bunch of other things. So let's return to our original guess that there's 1 write in progress and 10 read requests pending, waiting for that write to complete.
Yes.
So when the PG epoch changes, it is not enough for the write to be canceled. All the reads have to be canceled too. What's going to happen is that the write is going to get this interruption error signal, whatever. It's going to use that signal to drop its lock and requeue itself. Then the next read is going to get its lock, observe that the PG epoch has changed because it got the error signal, drop its lock, and requeue itself, and so on, up the chain.
Oh.
So they're all going to requeue. It's not just the write.
All the pending requests should do the same dance for waiting.
They absolutely must, because remember, they have pointers to the object context in memory state. That may not even be valid during the next epoch. They have to start over.
Let me be to be clear. By starting over, you mean they should check the PG status?
No, the no. The OSD goes back in the so we right now. There's so in classic OSD, there's an actual queue, right? What we do is we re-queue the op into the very central OSD op processing pipeline. The message itself, the original message. We drop all of the in-memory state for that request. For Crimson, it's a little more complicated because we don't have a queue like that. We have an implicit queue in the form of the pipelines. So what you should probably do is drop absolutely all of the state associated with the pipeline and go back to the beginning. The very first thing, where you pick up the PG lock and start from there. Or where you pick up the PG and start from there. Remember, after a PG state change, it might not even be the same PG.
At that very moment, we can ensure that the read request already have the PG, right? Because the right one already has the PG. We can assume that the read one should have the PG.
Yeah, they have a PG, but you don't know if that's true after the acting set change. You can't keep any in memory state over an interval change.
But in case of the acting set change, we can assume that it's just acting set change. It does not imply that the PG
primary change. No, Kifu, you would have to go through literally every check the primary does and make sure that it's invariant over an interval change, and they're not. After an interval change, recently written objects will typically be degraded. That's normal, because the replicas may not have seen the most recent I/O, so the primary is going to have to re-recover the current state of that object back to them, which means writes have to block, which means those reads needed to block earlier in the chain. They needed to block on wait for degraded object or whatever. I'm telling you, you don't want to play this game. You need to start the op processing pipeline over from the beginning. Do not remember anything from a previous interval.
Okay, I tried to be cut corner to save.
Yeah, it's that there are just too many different ways this can be difficult. One day in the future we might choose to be smarter about this, but yeah, it's not easy to do this correctly. It would be simpler and more effective, and in the common case, exactly as performant to simply requeue in that case. Mostly, you're going to have to perform the same checks in the same order anyway. So this
even though the PG this primary is still the same primary.
But think of all the things that aren't necessary.
The read request.
Yeah, the primary is clearly the same. But think of all the things that aren't necessarily the same. The object version could have changed. The current object context on disk could have changed. It doesn't seem like that's true, but it actually is. Because
Okay.
after peering, the authoritative PG log may have changed. That object may now be degraded. And with an erasure coded PG, it will go backwards in time, I promise. Because we roll back the unstable operations. So let's say after, like, when a PG interval change happens, there are 100 IOs outstanding on a PG. The primary has persisted them. None of the replicas has seen them yet. So when the OSD map goes out, changing the acting set but not the primary will be the only OSD with those 100 log entries. So during peering, we're going to compare those log entries to our peers. With a replicated PG, we're going to decide that all of those objects are degraded because the primary has a copy that no one else has. So before we can do anything to them, they have to be re-replicated over. And you'll notice the wait for degraded check actually does happen on a read request. Can situationally happen on a read request depending on whether it's write ordered. There is a lot of detail in Libratos' flags that change the way read and write ops are ordered. I really, really, really do not think it is a good idea to recheck all of these conditions, again, just to avoid what is frankly not an expensive operation, which only happens during peering anyway. So by the time we're even talking about this, we've gone to the trouble of doing 2 entire message round trips to the rest of the acting set, doing 2 entire commit cycles, and re-upping all of the primary state. Just having to redo a couple of lines of code in the op processing pipeline is small potatoes. So I think strongly that you should keep it as simple as possible. When we go through an interval change, every op goes all the way back to the beginning.
In the very beginning of the client requested handling.
As though it were a brand new message, read off the wire. You just have to be very careful about the order in which you do that, because they need to go back into all of those pipeline states in the same order. It's semantically identical to the order in which we call NQOP during interval change in the classic OSD. You'll notice we're very careful about which queues we look at and in what order.
We have to have a queue.
We don't. We have a queue already. That's what the pipeline state is.
Okay.
But I mean, if you look at the implementation, that's literally what it is. It uses that the C* lock, which internally is just a linked list of tasks. That's all it is.
It uses shared mutex, if I recall correctly.
Yeah, but in C*, it's just a linked list. There's nothing complicated going on there. It's a linked list of ordered waiters.
Okay, I'll check it out. Yes, that makes sense. It's safer.
So you have to requeue them, which basically means restarting them and making sure they hit the first pipeline stage in the order in which they need to be processed, which means you start with the ones that are furthest along and work backwards.
Yeah. To ensure that the oldest one gets served the first one first.
Yeah, that's right.
Those comes out of server. Okay.
Yeah, like I said, if you go look at classic OSD, you'll notice we're very careful about the order in which we call NQOP on all of the various wait queues. You're doing the same thing.
Actually, I try to avoid looking at it as a classic OSD.
I know that, but that particular piece of code evolved to where it is because we spent like years on sort of learning a good kind of discipline to think about this without constantly introducing mistakes, and this is what it looks like.
Okay, let's play safe at this phrase and try to counter later. And Chunmei.
Yeah, I'm still developing on the OMAP tree and finish the split entries and doing the make balance test case. And for the install error, and I made the problem on startup the Crimson cluster. So I have already saw who has already applied a PR to solve the problem. I will try to see if it is fixed. Okay, that's all.
Okay, thank you for firing the tracker ticket. And I believe it's a regression I introduced like a couple days ago. Sam.
Yep, I've been working on finishing up the PR for garbage collecting for basic garbage collection in CStore. So at this point, it can run. It should be able to run indefinitely, doing a random I/O workload without running out of space. So that's good. Because it will clean the used space behind itself. Right. So it should use about the amount of space that it's actually supposed to use, and not just sort of all of it. It's got a tunable that says like it has two tunables. One which is a target free space to maintain. So it won't allow, like, if it gets to that amount of free space, say 20% or something, it will garbage collect aggressively to maintain that amount of space or prevent IOs from happening. The other parameter is a ratio of used to unusable space. So at any point in time, we have segments that are available for writing because they're empty, segments that are unavailable writing because they have data in them, and then individual bytes that are actually live. That is the reference. They're real bytes. So if we have 2 megabytes of segments that are unavailable because we've written to them, but of those 2 megabytes, only 1 megabyte are actually live, and the threshold is set to 50%, it'll start garbage collecting that, even if the disk is relatively empty. This way, we won't get to 20% available space and suddenly garbage collect the entire disk. So in practice, this means that for the most part, we'll maintain only a fixed ratio over the real live usage of garbage space. But the disk should be mostly available for use. It's just a way to avoid a big flurry of garbage collection at the end. Go ahead.
So in other words, the other parameter is the ratio of the clean blocks versus the dirty blocks for choosing the victim segment to be garbage collected. Is that right?
No, that's actually an entirely different procedure. Right now, it just chooses whichever one has the most dead blocks. We can be smarter about that later. No, this is like when an IO comes in, we have to decide how much garbage collection work to do, right? And if let's say it's a 4 terabyte disk, but only 100 gigs are in use, arguably we shouldn't do any GC at all because the disk is mostly empty, right? But if we only have 100 gigs used, but 2 terabytes unusable, because we've done 2 terabytes of writes, I would argue we should have started garbage collecting a long time ago. So right now, with a 50% ratio on this parameter, if you have 100 gigs of genuinely used space, it'll start garbage collecting once there are 200 gigs of used segments. Because about 50% of the garbage collected space will then be free. But anyway, those are the 2 parameters that exist now. We'll probably want to make it smarter in the future, but the behavior seems to be deterministic at least, which is nice.
Okay. Thank you. Johan.
Last week I was debugging the interruptible feature, and I think I'll submit the PR as soon as this bug's developed. Okay, that's all for me.
Thank you. Yingxin?
Yeah, last week I have integrated GH objects and implement read and write to the old node root address in CStore. And currently I'm working at unit test of random insert with both dummy and the CStore backends, and I'm fixing related bugs.
Cool.
That's me. Thank you.
Kifu, how is the review on the part 1 of the dirty extent write-out going?
I think I can wrap it up by the end of this week, but I'm still struggling with it.
Okay.
Probably I could grab you if there is some questions later on.
Yeah. Do you want to speak after this, or it's up to you?
Later, probably later this week.
Okay.
Anything else? Nope. Okay. Talk later, and thank you. Have a good one.
Thank you.
you.
Right.